Okay, just looking at some equations, MC delta T, what's that mean? Well, again, we're having a problem with access to materials. So you got to remember back week before last to answer the question, but people did pretty well with this, okay? Remember, M was the mass of something, and delta T is the change in its temperature, right? And C, well, the example was we mixed two things of water. You don't really have to worry about C, you know, mix some cold water and some hot water. As long as water is boiling or something. You can really just say that the M delta T for one quantity of water and the M delta T for the other have to be equal and opposite by energy conservation. Okay, well, if it's concrete and water, well, concrete per unit of mass and per degree takes only about half of, actually a little less than half of the energy that water does, okay? In other words, when the concrete changes temperature, the energy change is only half as great as an equal mass of water. So that's what we call specific heat. You probably got that. So we've got to know that. So MC delta T mass, specific heat, change in temperature. And what do you get when you multiply all that out? Now the question is, what does it mean? Also, the change in heat energy, we're going to call that delta Q, quantity of heat. What does the equation? What does this equation express? What's it telling you? This expresses an isolated system, okay? There's no work by an external force. No heat gain or loss. From external source. And these are really really important principles for calorimetry. Okay, we talked a little bit more about that. Okay, so let's talk about this second equation. Okay, direct translation of this equation, sum of delta Qi equals 0. Well, a delta Q is a change in heat energy. A delta Qi means that you've got more than one thing exchanging heat energy, changing in heat energy. And if the sum of these is 0, well, that means this is what it says here. No external force, no exchange from outside. Okay? Means you have an isolated system. Okay? So that the way you get to that is just, you notice what delta Q means, it's a change in heat energy. It says you add up all the changes in heat energy, it's 0, meaning you're not getting any heat energy from outside. And no work is being done from outside. Okay? So, and this is an instance. Okay? Relate this if then your delta QI is delta Q1 plus delta Q2. But that's what you have up here. I didn't want to write that because I wanted you to think through what these things meant. This is a delta Q1. And this is a delta Q2. And if you have much more, you know, then 3C3, delta T3, LC, M2, M4, C4, delta T4, and so forth. So we developed this equation in the previous class, and everybody recognized what it was about. Okay, and I posed the question of, you know, how would you, if you have a piece of material, how do you determine the value of alpha? And I got a pretty good answer there. Well, L naught's the length it starts at, delta T is the change in temperature, and L is the length it ends at. So if you know the initial length and the final length and change in temperature, then you change this for, solve this for alpha. That's a very good answer. It's not quite a conceptual answer, okay? So conceptually, why does the equation work like this? Well, conceptually, the longer the thing is, the greater the length change. Now, we could rewrite the equation to get a little bit better handle on this. This is the change in the length, right? So change in length now, why does the thing change in length when you change its temperature? Well, if you heat it up, the particles that make it up, the atoms or the molecules within it, start moving more, start oscillating more. And it's quantum mechanical, and you know, this is kind of a non-rigorous explanation, but it kind of works. Okay, they got to move further apart. They need more elbows. Now they don't have elbows, so it's just totally an analogy. Okay, but as it turns out, they got to occupy a little more space. And the hotter they get, the more energetic their oscillations, and the more space they need. So to the extent that the change is linear, which it is over small temperature ranges, the change in length will be proportional to the change in temperature. Now, the more length you got, of course, the more molecules there are to move apart, the more molecular spacing between here and here. They move apart by the same amount, no matter how long the thing is. You have a given delta T. Okay. So the longer it is, the more delta L. The greater the delta T, the more delta L. And alpha is a measure of how much the rate with respect to length and change in temperature at which length changes. So alpha equals delta L over L naught, okay, which is the proportional change in length. All right, this is divided by delta T. Now I could have put the delta T in the denominator here, but I want to label this as proportional change in length. Into the temperature change. So alpha is directly proportional to length. The more particles you got, the greater your change in length. Okay? Then the more you length, the more particles you got. So it's a direct proportion for that reason. You need to understand proportionality to understand equations. You need more than that in many cases, but proportionality takes you a long ways toward understanding. Okay? Alpha is inversely proportional to delta T. Well, let's state that as the more delta T that's required for given delta L, less the value of L. When you think about that. Okay, so I commented that if these are areas, then you're going to have beta here, which is twice alpha. If these are volumes, you're going to have a gamma, which is 3 times alpha. And we talked last time in some detail how the binomial theorem and other things guarantees that for small changes in temperature, that works. Okay. Now, the next equation we want to look at is R equals Ka delta T over L. So we want to talk about what this means. And I'll also observe R or H. R would sometimes be the rate per unit area. Okay. So R could be H over area. I used R last time. And I'm actually going to go ahead now and change that to H because that's what your textbook, I believe, uses. Looking at the previous edition. As I say, they went and changed their notation. And For some unfathomable reason, didn't ask my permission. Okay, well, not like they didn't need it. I'll use HF. There's a good reason for it. Okay, so question is, what's all this mean? What situation does it apply to? Okay, well, we do pretty well. We recognize this as like a change in temperature per unit length of a bar. You got one end and the other end at different temperatures. Okay, so this is change in temperature, obviously. This is the length, and this is the cross-sectional area. So you got a bar here. This end is held at temperature T1. This at temperature T2. You got a length L. In the cross-sectional area, we'll say A sub CS. You know, we can put a CS on here, although you're not going to see that physically in the book, but just to remind you what that A is. It's a cross-sectional area. Okay, so obviously, if you have a greater temperature change between here and here, you're going to have a greater heat flow. And this is your heat current. Okay? It's the energy change. Well, we'll get to what that means. Okay. Now the delta T over L. The longer the bar, the less heat current you're going to have. If you're holding a short bar in the fire, your hand's going to warm up really fast. If you're on a long bar, your hand's going to warm up more slowly. There's less heat current. And the heat current is inversely proportional to the length. Okay, so it's proportional to delta T. Greater delta T, the more the heat flow. Inversely proportional to L because you have less temperature change per unit of length if you have a greater L. Greater the L, less the heat flow. And that's again intuitive. Or we could say it's proportional to delta T over L, which is the temperature gradient. Okay. This generalizes in the notation of multivariable calculus. You have a heat flow vector that's of the same form, except here you do the gradient of your temperature function. So I'm just going to write that down. Ka times the gradient of T. And I should understand multivariable calculus well enough to understand that. And yeah, not quite everybody does, but there it is. Okay. Well, heat flow is proportional to A because, of course, the thicker this bar, the more area you have for the heat to flow through. Now I could go into a little more detail. You take a little increment of this bar, and the heat flow across that increment is what it is. And the more of those increments you got over the cross-sectional area, the greater your heat flow. not gonna do that. In interest of time, but that's why I keep emphasizing you need to be able to think in terms of small increments. Understand physics, understand motor over calculus, etc. Okay. Okay. Depends on the material. If you have an insulating material, okay, small, and you have not much heat flow. It's kind of the way you want the walls in your house on a cold day or a hot day. Well, you want to understand that you have enough intuition. You should understand every detail of this. The H is the SI unit for watts. That's a rate of energy change, right? Watts is joules per second. Energy per unit of time. H is delta Q over delta T. Or in a variable situation, dQ dt. Okay, again, this is what we have. H ultimately has units of energy flow per unit of time, or watts. Okay, and K is what we call thermal conductivity. It depends on the material. Got a question, right? So that K has to have units of watts divided by units of length, because of course area divided by length has units of length, right? Per unit of temperature. Okay, so it could be watts per meter Kelvin, or joules per meter Kelvin second. A kilogram meters per meter squared per second squared for all that, and simplified. Okay, depends on what source you're looking at. So there you have it, but this is what it means. Okay, this is radiative heat transfer. E is emissivity. I wrote this down before. This is a Stefan Boltzmann constant. (5.67 times 10 to the negative 8 with the appropriate units, which are watts per square meter Kelvin to the fourth. And I commented that typically something that radiates heat or absorbs heat, depending on its relation to the surroundings. You have the heat flow from the object, like heat flow from your body, okay, radiating, okay, and heat flow coming in from the surroundings. You're radiating heat away, but you're getting heat in from your surroundings, and your surroundings always radiate some heat. Often not much. Like on a cold night, in the example I did, you're radiating away to the clouds. If the clouds are 200 Kelvin and you're at 300 Kelvin, then 300 to the fourth is about 10 times as much as 200 to the fourth. So you're radiating away 10 times as much heat as you're gaining. You're radiating away 90% of what you'd be radiating away if you were radiating away to absolute zero. So if your walls were all at absolute zero, of course, absolute zero is unachievable, and you're certainly not going to get that close to a bunch of walls, among other things that kind of destroy most walls. But thermodynamically, it's impossible to achieve absolute zero. But if you're in a room at absolute zero, you can at least imagine that. You'd be radiating away like 500 watts. And your body isn't going to maintain that. You maintain a 500 watt power output, you're in pretty good shape for 10, 20 minutes. And you collapse from exhaustion and freezing. Okay. So, no, basic message is don't run around naked in absolute zero. At least put a shirt on, right? A coat, good whole body suit, and you're still going to die. Okay. But more slowly, and that's not necessarily good. Okay. Well, I'm kind of out of time. So what I really talked about today is how you process situations that we talk about and how you understand the equation. The next time, that's something to really look forward to. You take a handful of these plastic beads and you fling them into a container and they can bounce around, right? They bounce around, they bounce off the walls, they bounce off of each other, they exchange momentum. Eventually they'll run out of energy. But these things maintain their energy pretty well. Because that one loses half its energy. Okay. And they bounce off each other. So well, that explains much of what happens in a gas, especially a gas of argon, which is one of the noble elements. Okay. It exists only as single molecules that basically behave like little balls. Okay, doesn't combine with other stuff. It doesn't form chemical bonds. You just got little balls. Oxygen behaves like if you got a bunch of those glued together in pairs. And that gets a lot more complicated because they can rotate, have energy rotation as well as energy translation. Monatomic gases, single atom gases, have only kinetic energy of translation. They don't want to have them be split. And we're going to analyze these collisions with walls and come up with the properties you observe when you try to find them in the gases, which will probably be some level of ice. Okay. Please do everything you can to get access as quickly as you can. Will do. And let me know that.
Okey-dokey.
I'm gonna try to get over and talk to the board. First. Okay.